Here we are with exercise 5 of chapter 14. Your goal here is simple. If the goal were so simple, why would there need to be so much text just to explain this? Okay. Write code to reproduce figure 14.5. So rather than read all of this words, I'm going to just show you the figure and explain what it means and what you are supposed to do. Okay, so we start with this matrix here. This is a 40 by 30 matrix, and you can see that it contains noise. So this is just smoothed noise. So you start with random numbers and you smooth it out. There's multiple ways that you can smooth random noise. There's tools in the image processing toolbox that you can use, but I chose to just create a two-dimensional Gaussian kernel and then convolve this image with that 2D Gaussian kernel. If you need a refresher on 2D convolution using Gaussians to smooth an image, you can refer back to I think it was chapter 12 about the applications of matrix multiplication and so on. Okay, so then you have this smoothed noise image, and then you take its singular value decomposition and show the three matrices that you see here. This is U, this is sigma, and this is V transpose. Now, it's pretty interesting to see that the first several columns in U and the first several rows in V transpose look very smooth. There aren't that many features or components or variation in them. And then as we get to later and later components that you see going to the right here and going down here, these correspond to the smaller and smaller singular values, which are approaching 0. Then you see that the vectors look more noisy, unpredictable, random. Here in panel B, you see what is called a scree plot. This is a term you might come across in statistics, for example, principal components analysis or factor analysis. They will call this thing a scree plot. It's named after Professor Scree. Just kidding. I don't know why they call it a scree plot. Okay, it's very simple. It just shows the singular values of the image or the data matrix plotted. So these values here correspond to the diagonal of the sigma matrix. It's that simple. I have converted this to variance explained, just to make it easier to interpret. So what does this mean? How do we think about all this in context of the image? So the first component here, or layer, accounts for around 30, 31, 32% of the variance or the dynamics in this image. So that means if we were to take the first column of U and the first column of V, which is the first row of V transpose here, so we take that column vector and the row vector, create an outer product between them, so that gives us a rank 1 matrix, and then scale it up by the first singular value, then that gives us a component or a layer. I call this a layer. And that you see visualized here. Now, this image here is accounting for about 30%, almost a third of all the variability in this image, just in the first layer. Okay, and then we take the second layer that accounts for, I don't know what this is, 26, 27% of the variance. And that means that if we take the outer product between the second column of U and the second row of V transpose multiplied by the second singular value, then that gives us the second layer or the second component, which here I call L1 for layer 1. Now, you can see each of these layers, they look slightly different from each other. They are accounting for different spatial patterns in this image. And then the idea down here of this lower row is we are just summing up the layers. So this is a cumulative sum of these layers. So this image here is the same as this. This one is the sum of layer 1 and 2, or layer index 0 and 1. So this image here is this thing plus this thing, nothing more than that, just the sum of these two layers. And remember, each of these layers is a component. It is a spatial pattern in the image, and it is created as the outer product between a column of U and a row in V transpose with the same index multiplied by the singular value of that index. And then what's really interesting about this image and smooth images in general is that it only takes a few components to pretty accurately reconstruct them. So if you look at this is just the sum of the first four layers. So it's only these four components here. This image and this image look really, really similar to each other. Not identical. You can see some differences here in this dark patch over here. It's only going to be identical when you do a full reconstruction, right? But when you look at this, you see we don't need this full reconstruction, right? We only need the first, yeah, maybe we could add another one or two layers, or maybe that's not even necessary. So this is all qualitative, comparing this original image to this composite image. That's qualitative. Here in this exercise, we are focusing on the theory. I want you to focus on the code and the computations to get this stuff to work. In the next chapter, in chapter 15, we're going to revisit this concept with real images and more quantification of the reconstruction accuracy between these low dimensional reconstructions and the original image. By the way, this is a technique that people use for denoising data sets and images. Okay, let me see. Oh yeah, the last thing I wanted to mention is don't worry about putting all of these subpanels in one plot. I didn't even do that. I made this as one figure, this as a separate figure, and this as a third figure. And then after creating these three figures in Python, I put them together in Inkscape. So focus on the code and the implementations of the linear algebra concepts. Don't worry too much about the exact visual niceties. Okay, so now I'm going to switch to Python. So here I create the matrix. This is actually just specifying the matrix sizes. Here is where I create the matrix. So it's just n by n random numbers, and then I convolve that with a 2D Gaussian, which looks like this. Now, if this looks unfamiliar or maybe a little bit familiar, but you forgot, then it's totally fine. You can refer back to uh, chapter 7 on matrix applications, in particular, where I talked about filtering and image filtering. Okay, and then here is the important part. I take the SVD of this smooth random numbers image. And yeah, well, as you know, the SVD in Python doesn't return the sigma matrix. It returns a vector of singular values, and that needs to be transformed into the sigma matrix. So then, yeah, I create a matrix of zeros and then fill in the diagonal. Okay, and then this is for panel A. So not super amazing, this code here. I'm just creating an image of these different matrices that you see here. Here is the code to create the scree plot. Earlier in the text in this chapter, I discuss why it is justified and also relevant to transform the singular values into percent variance explained. Here you see the formula. It's very simple. You just take S, so the singular value is divided by the sum of the singular values. This here gives you proportion of variance explained. And then, just for visual convenience, we multiply it by 100 to give a percent change, or percent variance accounted for. Okay, and now because these are random numbers, of course, the scree plot won't look exactly like the one I showed in the book, but you should get a pretty comparable qualitative scree plot dynamic. So you see it drops down pretty quickly, and then most of the components, most of these singular values are basically zero, just a hair above zero. And by the way, it's interesting to play around with this parameter here of the scaling of the Gaussian. So you can apply more scaling or less scaling, or no scaling whatsoever. That's something that I encourage you to explore on your own. Okay, and then here in this code, I'm creating panel C of the book figure. And yeah, let's see. So here in a for loop, I compute the outer product between the ith column in U and the ith column in V, which is the ith row in V transpose. So this is the rank 1 outer product matrix, and then I scale it up according to the corresponding singular value. So that gives me one layer. Here I call it rank 1 matrices, rank 1 mats. Okay, so then let's see, I'm showing only that layer. And then here's the sum of all the layers. So this is the sum of the layers over the first axis from the beginning, so from the first layer up until the current layer. And then the plus 1 is, just for indexing purposes. Okay, so then let's see. Uh, you have to remember this. So stare at this image here and let it burn itself into your retina. And then we go down here and compare it to this. And I already lost it. So I couldn't really say how good of a reconstruction that is qualitatively. If you like, you could add a little bit of extra code or create another figure to plot those two side by side, the original image and this one, the sum of layers 0 through 3. But again, for this exercise, we're really just focusing on the theory and writing the code. In the next chapter, we are going to explore this more quantitatively using real images.